Okay, now with those previous videos we've reviewed the lift force, the drag force, and we just have gravity to review now. So gravity force, we can call this the force due to gravity. We frequently write it as W, as the weight. W is equal to the mass times the acceleration due to gravity at the surface of the Earth. So here is the mass, and this thing is the gravity. And this is at Earth's surface. This is 9.81 meters per second squared. So weight, that's a pretty simple concept, just pretty much depends on your mass. This thing never really changes. Actually, it does change as a function of your radius outward from the center of the Earth, but for all intents and purposes, for here, we can just refer to this as essentially a constant. So once we have our forces on our vehicle, and we represent our vehicle as a point mass, we say, oh, okay, here is the weight force, here is, say, lift, and if you had to guess, because we know that lift is parallel or is perpendicular to the velocity force, we know that velocity is going this direction, so that means the drag is going in this direction. So with these three forces, we can come up with our acceleration. Our acceleration is just going to be the sum of the forces, and this is just summation notation, all divided by the vehicle mass. So this comes from F equals ma, so we can just say that A then is just F divided by m when we rearrange the equation. That's kind of a lousy m. Let me redo that. M. So this is just kind of the more, this is the vector form of it. What we do is we just say that if we sum up all of the forces, the drag force, the lift force, and the weight force, then we divide that by the mass of the vehicle, we get the acceleration of the particle that represents the vehicle. Once we have that, then we can predict position, and we can do that with simple calculus. So an approximation, you could say, is that, well, we know the forces, we can calculate that based on our current altitude and our current speed and stuff like that. We know how much we weigh and stuff, so we can predict the lift, the drag, and the weight of our current location. So great, we now have the acceleration. For our acceleration, we would say, okay, our previous velocity, or our next velocity, so our velocity at the next time step, which I'm calling the I plus 1, is just our current velocity vector plus our acceleration, which comes from up here, we calculate that up there, so we know this, times some delta t. This delta t is just a small time step. Small time step. So we know this is our previous acceleration, or our previous velocity. Here's our current acceleration, and here is our small delta time. Normally people set this to something to be like 0.01, and then we put this into a computer and it computes what the velocities are. So not only can we compute what the new velocity should be based on our current acceleration, but we can also calculate our new position. And our position vector, we normally call it r. And I'm not exactly sure why. Probably it has something to do with the fact that it's a radius vector from the center of the Earth. So we'll just say that r, their next r, so r plus 1, is just equal to our current r plus our current vi times some delta t. This is the exact same delta t right here. So what we have here, okay, just separate that out. So we can say from our acceleration we can compute a new velocity. With this new velocity as a result, we can compute this new position. And this is really swell, because then we can put this in a computer and we can say, okay, after we compute our accelerations for where we currently are, and then we compute our new velocity, compute our new position, then we just take a small step forward with this delta t. Then at the new step we feed back all this information and we compute it up here, back in our forces, and we compute a new acceleration, because as we change our velocity and we change our position, we're going to feel different forces. If we change our altitude, for example, we'll have a different density in the atmosphere. If we change our velocity, we'll experience a different speed, which affects our lift and our drag. So we might start having different lift and drag numbers, and in general our weight will stay the same, assuming that our mass is not changing as we fly. But we can put this into a computer, so we can, if you're familiar with computer programming, you could say that, you know, while we could say while our t, our time, is less than our max time, we could say it like that, and we say, oh, at first, t is 0. Then we compute our acceleration from our forces divided by mass, then update our radius and our velocity vector, and update our time. So time will be equal to time plus that delta time. And then that's the end of the loop. What we do then is we say at the very beginning we have to specify some initial conditions for our radius vector and our velocity vector right here. So we might start out saying, oh, our initial position is some vector of blah, comma, blah, comma, blah. That's supposed to be a comma. And likewise for our velocity vector. So here's equal to something, something, something. Okay, so that represents how we initialize this loop. And then what we do is we just update our position with these little small time step increments, and then we can predict where the vehicle is going to go. Now, doing this type of a method where we just say, vi, the next velocity vector, is just equal to the current one plus our current acceleration times some small delta t, this is actually called Euler integration. Euler integration. So there was this famous mathematician a long time ago named Leonhard Euler, and he was a very, very smart guy, and he came up with this method that you could approximate these differential equations if you just incremented them slowly, one step at a time. So some small time step, compute the new forces, update all the state information. This stuff is frequently called the state, and sometimes called the state vector. And so all it essentially is, it says, okay, we can say x, whatever our state is our previous x, or x of I plus 1 is equal to our previous x plus our x dot times some delta t, where x dot, that dot notation represents rate. So this is rate of change of x with respect to time. So this is also, if you're familiar with calculus, if you're pretty handy, you could just say it is dx dt. There we go. So that is one way of integrating. Another, this is pretty fast. It's pretty fast, and it's okay. It's very simple because we can see, oh well, it's very easy. We just take our current rate. This is essentially just our acceleration, and we times it by some small time step, and we get our new state. It's pretty straightforward. But it turns out this has some problems. This is not very accurate. So frequently it's not used because of it's not very accurate at all. So instead, what frequently gets used is an integrator scheme called the Runge-Kutta fourth order, the integrator. And frequently people call this RK4 as a shorthand. And we will talk more about this integrator in the next step. But we will find out how it's much better than this one, and it's much more accurate, and it's more expensive to compute than this, meaning that it takes longer in the computer, but it turns out to be much more accurate, which is really what we're looking for. See you next time.